All right, we're going to dive into a force that is absolutely fundamental to engineering, something that powers our world in ways you probably don't even think about. We're talking about torsion.
I mean, really think about it. You've got this engine, right? Creating all this power up front. And then you have the wheels, way at the back, spinning like crazy. So what's connecting them? How does all that rotational energy get from point A to point B?
Well, the answer is this one single powerful concept, torsion. It's that twisting force that makes everything from the drive shaft in your car to a massive wind turbine actually work.
Okay, so what is actually going on inside a drive shaft or any object when we put it under torsion? Let's break it down.
So, the official definition says torsion is the twisting of an object caused by a moment. And really, all that means is you have a rotational force that's being applied along the length of an object, kind of like you're wringing out a towel.
And that specific rotational force, that moment, it has its own special name, torque. So whenever you hear torque, just think of that as the cause. It's the action that creates the twist. You know, to really visualize what's happening inside the material, let's try a little thought experiment. Picture a solid metal bar, but imagine it's made of countless paper-thin discs, all stacked together like a roll of coins. Now, when we apply that torque, those discs don't get warped or bent out of shape. Nope, they just rotate, sliding a tiny bit relative to the one next to it. And that straight line we drew, it turns into a perfect spiral, a helix, wrapping around the bar. So we can see the twist, which is cool, but how do we actually measure it? How can we predict it? Well, that's where the formulas come in. The total amount of rotation, from one end of that bar all the way to the other, is what engineers call the angle of twist. We use the Greek letter phi for that. And that is the main thing we want to calculate.
So, what makes something twist more or less? Well, it boils down to four things, and the first one is pretty obvious. The more torque, or T, you apply, the more twist you're going to get. Makes sense, right?
The second thing is the object's length, L. You know this intuitively. It's way easier to wring out a long towel than a short, stubby one. Same idea here. A longer bar will twist more easily.
Third is something called the shear modulus, or G. This has nothing to do with size or shape. It's all about the material itself. You can think of it as the material's inherent stiffness, its stubbornness against being twisted. Steel has a much higher G than, say, aluminum. And number 4 is J, the polar moment of inertia. Now, this one is all about the shape of the cross-section. A big, thick, chunky bar is going to have a high J, and it's going to resist twisting way more than a thin, skinny one. And here is where it all comes together in this beautiful equation. The angle of twist, phi, is just the torque times the length divided by the material's stiffness, G, times the shape's resistance, J. With this, we can predict exactly how much any shaft will twist under a load. It's incredibly powerful. Okay, so that's the big picture deformation. But what's happening deep down inside the material? What are the tiny internal forces that are actually at play here?
So if you could zoom way in on the surface of the bar and draw a little, tiny, perfect rectangle, when you apply the torque, you'd see that rectangle get skewed into a parallelogram. That angular distortion, that's what we call shear strain.
Now that strain creates an internal stress. But here's the really crucial part. The stress is not the same everywhere. It's actually zero right at the dead center of the bar, and it increases in a straight line up to its absolute maximum value on the very outer surface.
And of course, there's a simple, elegant little equation for it. The shear stress at any point, we call it tau, is just the torque times rho, which is the distance from the center, all divided by J, that same polar moment of inertia we saw before.
Now, knowing how that stress is distributed isn't just some fun fact. It's the key that lets engineers design parts that are both incredibly strong and incredibly lightweight. And here's the big payoff. Since the middle of a solid shaft carries almost no stress, all that material in the core is basically just dead weight. So by making the shaft hollow, we get rid of that useless material and create something that is way more efficient at carrying torque for its weight. Of course, in the real world, it's rarely just one simple shaft. You'll have multiple gears and torques all along the length. To figure that out, engineers follow a pretty simple process. They draw it out, make imaginary cuts between the gears, and then use basic physics to find the internal torque in each little section. So, what happens when you push it too far? What happens when the stress becomes too much for the material to handle? Well, how things break under torsion is actually fascinating.
Check out this contrast. A ductile material, like steel, it fails where the shear stress is highest, so you get this clean, flat break, straight across. But a brittle material, like cast iron, it's actually weak in tension, so it fails where the tensile stress is highest, which creates this jagged, 45-degree angle fracture. Two totally different looks.
So there you have it. We've seen how torque creates a twist, how stress builds up inside, and even how different materials fail. These principles are running behind the scenes in so much of our world. So the only real question left is, now that you know this, what are you going to do with it?